Okay, to wrap up circuit analysis, we talk about our last topic, finding total power factor. First, there's a few things we have to keep in mind. At minimum, we need to be given information per impedance. Plus, total power factor is not the same as power factor 1 plus power factor 2 plus so on and so forth. I have to emphasize this because if you get that a power factor violates this situation, you're claiming that you're generating more power than you're inputting in. And in which case, if it was the situation, maybe perhaps you can contact the science committee, talk about the fact that you generated or that you violated you know, a universal law. And then you can probably say, finally, okay, so keep this two pieces of information in mind. You need to be given two pieces of information per impedance, and that the total power factor is not equal to the sum of the power factors. So let's talk about it. So, what do you really need to do? The goal is to find complex power. S equals to P plus JQ. Now, why find total power factor? Because the angle of the power factor is theta. So it's the angle of, well, angle of S, which is equal to tangent inverse of Q divided by P. And there you go. That's just what we need to do as a goal. So let's do that. It doesn't matter what kind of system you're given. When you're evaluating power, you sum up all the real power, you sum up all the reactive power, and that'll be okay. So let's say we're given the system. I tell you that power factor here is maybe 0.8 leading, and then maybe I tell you it's 100 watts. Okay, I gave you two pieces of information. Here I tell you S is equal to 10 minus J 20. And then maybe power factor is zero point 0.4. Or rather, if I tell you the complex power, you are given two pieces of information already. So no need for giving power factor. Okay, so I give you now power factor is equal to 0.8 lagging. And then that there's 100, let's do 500. 500 var is consumed. And just to make our uh, quantities a little more interesting, 10 volt amp with a power factor 10 volt amp, and maybe you can talk about 10 watts consumed. Okay, so first things first, find P, find total P. Second, find total Q. Third, S is equal to P plus JQ, and then these are total. find theta. Compute cosine of theta total equals PF total, and based on whether or not it's greater than 0 or less than 0, say it's leading, or sorry, say it's lagging or leading respectively. Okay, so given all this information, let's do that. So let's call this 1, 2, and 3. For first case, we have Q equals to 500 var, and we're given the power factor as 0.8 lagging. Because lagging indicates that the angle is going to be greater than 0, if we were to take this, it would be cosine of 0.8, and this will give us roughly, so doing that calculation, you get about 36.87 degrees. Okay, that's fine. Now, the relationship Q divided by P was equal to tangent. So therefore Q was equal to P tangent of theta. In this case, of this angle. So P is equal to 500 divided by tangent of 36.87 degrees. So if we do that, we have 500 divided by tangent of 36.87 degrees. We get about 666.66 watts. Lots of sixes. Okay. So now we're done. Let's call this Q1 and this is P1. Now let's take a look at the second quantity. So we have 0.8 power factor leading and 100 watts. So power is already 100 watts. That's given. But we have P. PF is equal to 0.8 leading. Based on this situation, theta is actually going to be negative. So we get 36.87 degrees. That's negative. So that means that Q being equal to P tangent of theta is going to be Q2, and this is 2, equal to 100 watts times tangent of negative 36.87 degrees. So we compute that quantity, we get about negative 75 var, which is okay for reactive power, but not okay for real power. Now for number 3, we're given 10 volt amp and 10 watts. So we have P apparent equal to 10 volt amps and P is equal to 10 watts. We can relate the two like so. We get P apparent cosine of theta. So we get a power factor of 1 because of this relationship. That actually tells us right away that Q is going to be 0. Because if we take the angle of this is 0 degrees. And that means that if we plug it into here, Q is equal to P apparent sine of 0 degrees. This just becomes 0 bar. So this system is probably the perfect one. Okay, so now all we have to do is add these quantities together. So P is equal to P1 plus P2 plus P3. Q is equal to Q1 plus Q2 plus Q3. If we do this computation, we should get we should get 776.66. And then from here, we have 500 plus or minus 75 plus 0. So we get 425. This is watts and this is var. From here, we just find the angle. So we have 425 divided by 776.66. And this returns us our total angle. So once we do that computation, we should get about 28.69 degrees. Okay. From here, our power factor total is just cosine of 28.69 degrees, which is roughly 0.87 or 0.88. Very close to 1, and therefore this system is pretty good. So there's some improvements we can definitely make on it. But this is how we find total power factor. We follow this 4-step procedure, and at minimum, each of these boxes have to encode 2 pieces of information that allow you to find total average power and total reactive power. So you can plug it in to find the angle. And based on what this is, because this is greater than 0, this is lagging. So we have a more inductive system compared to a more capacitive system. Okay? Thank you. And that's the end of the circuit analysis. Okay.